Welcome to this video in which we will discuss how to actually choose the reinforcement for strength and when meeting other requirements. So summary, reinforcement has to satisfy in the same way that we did one-way slabs, for example, temperature and shrinkage requirements, maximum spacing requirements, and also strength requirements, For example, for temperature shrinkage, the requirement is the same as the one we used for one-way slabs. The area of steel provided has to be bigger than 0.002 times the cross section area of the slab, which in this case is the thickness of the slab times the width of the slab. Now, for drop panels, we are going to be using the drop height, the drop thickness, and B is the column or middle design strip width, So whichever strip we are designing at that point, that's the B that we are going to use. If we are doing the complete design strip with column and middle strips there, that will be our B, or you can do it separately, You can do it separately. You may include top and bottom steel if both are present in the given section you are checking as area of steel that counts for temperature and shrinkage, and this is, you do it in one direction and then the other, Remember, you have to do protect the two directions. Maximum spacing, Maximum spacing of the reinforcement. Remember, we had this requirement before. Now we have different regions, Now, the most important, and then this is in line with what we just discussed, that inside of the column strip, there is a more critical area called the bandwidth. Well, negative reinforcement, Negative reinforcement in the bandwidth, BB, The maximum spacing of the reinforcement is 1.5 times HS, which is the thickness of the slab, and that has to be less than 250 mils anyway. Remember, the corresponding requirement in one-way slabs was 500, Not more than 500 mils in one way, but the bandwidth BB is more critical, so we limit that maximum spacing to 250 mils. Now, remaining negative reinforcement, Remaining negative reinforcement not in the bandwidth, that can be spaced at 3.0 or 3 times the thickness of the slab, No more than 500 mils. And positive reinforcement everywhere, 3 times the thickness of the slab, and has to be less than 500 mils, These two requirements are the same as in one-way slabs, So when it's a time to choose the reinforcement, for moment resistance, we are going to choose or follow the same process as the one that we did for beams and one-way slabs, In this case, generally safe to start with one layer of 15 bars in each direction for initial design, And if the calculated spacing is small, 100 millimeter or less, we are going to increase the rebar size, Cover requirements for two-way slabs are the same as in one-way slabs. And if we are thinking, for strength, how to get that amount of steel, we are going to use the same simplified process before, We may assume a moment arm of 0.92D, We used 0.9D before for beams, and then, once we assume that moment arm, if we make the resisting moment equal to the factor moment, we end up with an equation in which the only unknown is the area of steel, And then we provide it with the size of the rebar and the actual clear cover. We have to recalculate the resisting moment and check that it is indeed bigger than the factor moment, And we check that the steel yields, We check that the steel yields with the check that C over D has to be less than 0.8, 700 divided by 700 plus Fy. Remember always to check that the strain still is good, right? We have to check, right, both column and middle strips separately, right? We'll have different moments acting on them, right? So we have to do a separate checks, right? So about D, right? About D, because in these two-way slab systems, right, we are going to have steel running in the two directions. So which D to use, right, or which D to consider? So we are going to be able, right, in a given building, right? These are the column lines, right? We are going to have steel that has to go in this direction, and then we are going to have steel that goes. That's for the analysis in that direction. And then when we analyze this direction and the moments that go with this direction, then we are going to have steel running in this direction. So, which steel, right? In the thickness of the slab, right? You have to choose which steel goes in the outer, right, or in the farthest with the farthest moment arm, right? So which one do you choose, right? So is it the horizontal here? This horizontal steel, the one that goes in the bottom? Or is it the opposite? Is it the vertical steel, the one that goes in the bottom? Well, right, longer spans develop larger moments, right? Longer spans develop larger moments. Let me just erase my drawing here. So longer spans develop larger moments, and then they will require a larger moment arm. So when you have the largest static moment, right, or you have the largest spans, you are going to try to put those rebars, right, as farther away as you can, right, so you can have the biggest moment arm, right? So for example, here I have three different D's, right? D for the longer spans, D for the shorter span, right, and then the D for shear, right? The D that you'll use in the calculation of dV, right, could be the average of the two, right? So in the next slide, right, I have the specific mention to this. So for the long direction, right, the long direction, let me just probably rewrite this better here. So we had it, yeah, we had it on top, right? So for example, I have top reinforcement there. So in the long direction, right, D is H minus the clear cover, of course, minus the clear cover, minus the diameter of the bar by 2, right? And in the short direction, right, is this D, this is D short. We have D equal to H minus the cover minus 1 time the diameter of the bar minus half the diameter of the bar, so 3/2 diameter of the bar, and then D is the average of these two above, right? The D for shear is the average of the two above, right? While for flat slabs with drop panels, right, D will be larger, right, for the needed reinforcement, right? You have to be aware that now the thickness will increase, right, will increase. Perfect. So when we recheck the moment resistance, right, and we have the location of the bars, right, the real location, right, our B will be, of course, the B that corresponds to the column strip or the middle strip that we are checking, right? We calculate A, which is the depth of the compressive block. We calculate the moment resistance, and then we check that this guy is bigger than the factor moment, right? And we check that the steel yields, right, with this relationship. So just to summarize, we saw how much steel we need for shrinkage and temperature, and now we know how much steel we need for strength, right? We are going to use the greatest of the two quantities, right? The greatest of the two. What about reinforcement detailing, right? The one you love, right? Cutoffs and clear cover and all that stuff. Well, the first step is clear cover, which is the same as for slabs, right? For slabs. So 20 mils if normal exposure, and 40 mils, right, if it's freeze and thaw, right? And then there is the other column that is not shown here, the one for chlorides, right? Chloride attack. You have to meet, right, these requirements, right, as well, right? 1 times the diameter of the bar, right, this one, and then 1 time the cover to maximum aggregate size for normal exposure, right? Of course, you see for freeze and thaw and sulfates, right, you have a bit of a bigger clear cover. What about anchorage, right? What about anchorage? So, for example, positive moment, right, perpendicular to a slab edge, right? So at the end of the slab, right, must be embedded 150 mils into the spandrel, beams, columns, or walls, right, at the end of that slab. So at least penetration of 150 mils for positive reinforcement, right? If it's a spandrel beam or a column, you have to embed that steel at least 150 mils, right? Negative reinforcement has to be hooked, right? Either hooked or otherwise anchored into those end elements, right? Spandrel beams, columns, or walls, right? To secure development, right? Development of these elements. If you have a slab that ends up in a kind of a cantilever, right? You still have to continue those rebars, right? All the way to the end of that cantilever, right? Both top and bottom reinforcement have to be extended, right? And you have to still provide cover, right? So curtailment, right? Curtailment of reinforcement, cutoffs, the part that you love, right? Well, good news, right? Good news. We don't have to do the curtailment with the detailed procedure that we learned. We're going to be using these tables, right? These tables. If your slab is well behaved, right? It's a regular slab, then you can use these rules, right? So I have flat plates without drop panels and flat plates, right, with drop panels for the exterior span or the exterior end, and then interior, right, interior detailing. Well, at this point, let me just show you what this table has, right? First of all, right, requirements for the column strip, right? Top steel and bottom steel. Here it says at least 50% of the steel, right, has to meet these requirements, right, and the remainder has to meet these requirements, right? And then for the bottom steel, for example, at least 50% has to meet these requirements, and the rest of the steel, right, has to meet these requirements, right, in the bottom row, right? And those requirements are, right, for example, good anchoring for the top steel, right, and then the cutoffs for the two types of steel, right, here and here, right, for instance, right. Well, you see that at least 50% has to have greater embedment, for example, right, and the rest it could have less embedment if you want. For the bottom steel, right, at least the 50% here, this one over here, right, has to continue, right, all the way, you see, has to continue into the interior support, and the remainder, right, doesn't have to have that, right, but it cannot be too far from the support, you see. It has to be at least at a maximum of 0.125 the direction or the distance, the length of the span in consideration, right? And then you did that for the column strip and the middle strip, right? And these requirements are the same, right? But a bit more relaxed, because the middle strip will have less moments, right? Less moments. So this is how you read this table, right? You read this table. So well, you follow the table, you'll be okay, right? Integrity reinforcement, right? This is such an important reinforcement, right? It just prevents the slabs punching through the column and falling like a pancake. Well, this is actually going to protect, even if you fail on that connection between column and slab, this is going to help preventing that pancaking failure, right? One slab falling into the other and then just adding weight until you have a complete collapse of your building, right? So when failure of these slab systems happen, right, these bars are going to be ineffective, you see? These are going to be pulled out from the concrete, right? they become useless, right? And only the bottom steel, right? Only the bottom steel is the one that is going to be holding up the system, right? Holding up the system because they are still encased into concrete. So integrity reinforcement is going to be intended to prevent progressive collapse, right? Either one section or the whole thing just goes on you, right? If the slab fails, it can still be held up by catenary action, right? Catenary action between the supports. So essentially, just the slab hanging from the rebars, right? And you see those that catenary action on a suspension bridge, right? So these bottom bars are going to be doing what the cables, right, in that suspension bridge are doing, right? So the requirements, right? A minimum of 2 bottom bars, right, anchored to the column core or capital, right, in each span direction. So a minimum of 2 bottom bars in each span direction. Now, the area of integrity steel, right, in all faces, including exterior faces, right, at the column edge must be at least, right, the area of integrity steel has to be equal to 2 times of the specified shear at the interface, right, at the interface. Specified means not factored, right, not factored at the ultimate state, but just specified just at the service state, right? And it cannot be less, right, that amount of shear, it cannot be less than twice the slab self weight, right? So twice the slab self weight is the minimum load that has to be included to calculate the integrity reinforcement, right? Now, the integrity reinforcement does not need to be extra bars, right? Bottom flexural bars can be used as integrity steel, right? And it has to look like this, right? That's a plan view, right? In plan view, you see the bars just crossing towards that column, right? Just crossing through, right? In elevation, right? If you're going to be splicing these bars, right, they have to look like this detail, right? At least the development length, right, for the splices, right? And then the integrity reinforcement will allow you to contain that undesired behavior, right? So last thing to consider about the slabs, right? You have to design the 2 directions, right? We don't want to fall into that shortcoming, right? That happened 100 years ago, in which your slabs were under-designed, right? How do designs change from one direction to the next? Well, the spans will change, right? The moments will change, and the middle strips will change size, right? V will change from one direction to the next. L1 and L2 will swap, right? As will C1 and C2. These guys were the column dimensions, remember? So perfect. This is all for this topic. In the next video, we will do an actual example, right? An actual example, and we will put all these concepts to work. Thank you very much.